Hello friends, in this video we are going to unbox my Holzmann lathe, take some measurements, and I will show you the build quality and surface finishes. We'll also do an upgrade and I will show you how I got the Spindle Runout down to about 5 microns without spending a single penny. If you are interested in a specific part of this video, feel free to use the timestamps. Just to be clear, this video is not a step-by-step guide, it is just my personal experience with this lathe. Enjoy watching. The lathe comes in a wooden crate, wrapped in protective film. I decided to start by taking out the user manual. All the feeds move smoothly. The lathe is generously coated with protective grease. Let's take a look at the belts and gears. The belts are quite thin, and the gears are heavily greased with some really thick grease, probably to prevent noise during operation. The key in the chuck turns stiffly, but I would actually call that a plus rather than a minus. The accessories are standard for this type of lathe. There are reverse jaws, an oil can, a set of wrenches, a set of lead screw gears, a couple of screwdrivers, a set of hex keys, an MT3 center and MT2 center. Now I'm going to take some measurements. I'm not sure if I need to comment on everything here. I think you will be able to see everything for yourselves. Measuring the rotation of the headstock relative to the lathe bed. Don't pay attention to the runout. We set the indicator so that deviations on the plus and minus sides near the chuck are the same. Moving the indicator further from the chuck and see how unequal the deviations are. We can see the deviations in one direction are 0.15 of a millimeter and in other direction 0.13 of a millimeter. This means that the headstock is rotated by 0.02 of a millimeter over 150 millimeter lever length relative to the lathe bed. Do the same measurement in vertical plane. The difference in readings is 0.07 of a millimeter. This means that over a 150 millimeter lever, the headstock is tilted by 0.07 relative to the lathe bed. Tailstock tilt is 0.03 of a millimeter over 50 millimeters. Tailstock rotation is 0.11 of a millimeter over 50 millimeters. Here is what the electrical part of this lathe looks like. The grounding bolts are not tightened at the factory. Apparently it is fine like this. Let's start the upgrade. The main problem with this lathe is that the bed under the headstock bends, which seriously affects the overall rigidity of the machine. I press on a part in the chuck with 150 mm lever. Watch the force and see how much the chuck moves. We can see that with a force of 45 newtons, the spindle moved about 0.02 of a millimeter. Let's remember these numbers. Since I don't have a powerful angle grinder to make a plate from a solid steel piece, I decided to build truss here from a 14 mm round rod. I carefully adjusted the rods to the bed and to each other. For the truss to work, the rods must press against the bed and also against each other. Drilling the bed was very difficult. I used a carbide drill bit. I taped threads in the rods. Everything will be assembled with M6 screws. Installing the spacers. For some reason I decided to put epoxy in the contact points. I know it does not help, but it seemed better than nothing. I tried to use the indicator so that the bed would not deform while installing the spacers, but that was impossible. The bed was slightly bent upward. Here is the resulting contact area. I scraped the headstock to the bed to achieve good contact. At the same time, I tried to control the tilt and rotation of the headstock. This is how the contact looks now. I think it is not bad. I installed the headstock and now let's measure the chuck deflection again. We see about 1.5 hundredths of a millimeter. Previously, it was 0.02 of a millimeter. Can I say that rigidity increased by 25%? Now the electrical box is lifted and the motor is moved back and mounted with 3 bolts. I did not change the belts and pulleys. Time to work on the cross slide. You can hear how it wobbles on the bed. This is what its contact surface looks like. I think comments are unnecessary here as well. The contact area looked like this before. I didn't like it. I scraped the surfaces while controlling the rotation of the carriage relative to the bed. Now the contact area looked like this. Let's work on the cross feed. I have a surface plate of approximately class 1 accuracy. I will use it as a reference. This is what the contact surface of the cross feed looks like. Here is the scraping process. Now the contact area after scraping looks like this. Next, I need to scrape the cross feed surface on the carriage, using the cross feed itself as a reference. This is the result I got. Trying to measure the guide misalignment. There is a dip of 0.03 of a millimeter in the middle. I decided not to touch it because scraping that area would be very difficult. Scraping the surface for the compound slide. I got carried away and did some decorative scraping. The parts of the compound slide also need to be scraped. Any loose contact can cause play and vibrations during operation. I also didn't like the contact surfaces of the tailstock. Now they look good. If you remember, the tailstock was rotated by 0.11 of a millimeter. We need to fix this. Now everything looks fine. At this stage we can assemble the lathe, but not completely. There is one more important upgrade we need to do. We are going to make adjustable clamping bars for the carriage. For this, I need to mill the stock bars. Since I only have this lathe, we will mill them on it. The carriage was clamped to the bed. I clamped the bar in the tool holder and I used a 12mm end mill. It would have been better to use bronze, but I found a ready-made brass strip, 10 by 3mm in cross section. Drilling holes in the bars and tap M4 threads for the clamping screws. Installing the carriage. Now it is already final. Installing the upgraded bars. In the brass bars, I made slots for the clamping screws, so that the bars don't move during operation. Installing the bars in their places and adjust the clamping screws. Installing all remaining parts. It is time to take off the protective film. Everything moves without play and without sticking. I would actually call it perfect. However, the surface finish after turning disappointed me. Look at this spiral on the parts. It does not match the pitch of the automatic feed nor the lead screw pitch. I checked the entire lathe again. I tried to find the problem in my own handling. I thought I had made a mistake somewhere. I tried different cutting modes and materials, but the problem remained. The cause was in the spindle bearings. I turned it apart and measured its runout with an indicator. I did not rechuck the part. You can see that at 300 degrees on the chuck, the indicator shows about 7 microns. Now I will rotate the chuck exactly one full turn. Again 300 degrees on the chuck, the indicator now shows about 1 to 2 microns. This tells us that the rollers inside the bearing are slightly larger on the one side than the other. As they roll, they move the spindle. In this photo, you can see how I pressed out the spindle using bolts and nuts. Inside the bearings, I found traces of sand. This is what the lathe spindle looks like. You can see the bearing markings here. In my case, the bearing near the chuck has accuracy class P5 and the bearing near the drive pulley has accuracy class P6. This is how I pressed out the bearing closest to the chuck. I disassembled and cleaned the bearings, built a stand to measure the diameter of the rollers and sorted the rollers of the same diameter into groups. The idea is to arrange the rollers inside the bearing to minimize runout. I asked an AI to calculate the position of each roller in the bearing cage to minimize runout, and it gave me this table. I assembled the bearings according to this table. To fit the bearing onto the spindle, I heated the bearing in the oven to 120 degrees and cooled the spindle in the freezer. The result exceeded all my expectations. Look at these macro photos of the surface after turning. Let me remind you what the surface looked like before reassembling the bearings. Look at this beauty. The spindle runout is about 5 microns, maybe even less. Let's look at the official tolerance tables for the super precision NSK bearings. The top table is for P5 grade bearings. The bottom table is for P4 grade bearings. From this, we can conclude that by simply sorting the rollers in P6 and P5 bearings, I got bearings very close to P4 class precision without spending any extra money. At this stage, my lathe upgrade is complete. It took about a month of work in the evenings. I hope I was able to show you something you have not seen before. I wish you to enjoy whatever you are doing, even if it is just scraping. See you soon!